So let's prove some lower bounds. Okay, so here is a plan. Now we kind of showed some barriers in these two models. Now we'll prove lower bound for the group model. It extends to semi-group model as well. So let me first introduce the range counting problem. And in fact, Kasper introduced it 2 days ago when he was presenting the multi-phase open problem. So range counting is I'm giving you a bunch of points, maybe in 2 dimensions, maybe in like some d dimensions. Every point gets a weight, and say weight is an element of a group. Now, again, it's a static data structure. You know all the queries in advance, and every query is just some region, some shape. For example, it might be a triangle. The query asks you to compute the sum of all the points inside this range. The group elements, you sum them up, give me the answer. Another query, you know it in advance, the shape. You don't know the input points and their weights in advance. Sum them up and give me the answer. That's some group element. And so yeah, let me remind you how Kasper defined it as I know a linear problem. So we have some. That's a bad marker, right? We have some set of regions. Where is it? Red and blue markers. I used to have good markers.
There are 2 blue.
I found them. Okay, so range counting problem is defined by a set of ranges. So it's some capital R, set of Ri's, say i's from 1 to m, such that each Ri is just a subset of a d-dimensional Euclidean space. Those are ranges which will be queried. And then for every set of points, for every set of points, each of them is a point in Rd, and for every set of weights of these points, each of them some group element. We wanna answer this query. So for every set of points, this range counting problem just becomes I can just define the following incidence matrix for this problem. For this x, I just define a matrix which has numbers like rows 1 to the number of ranges, usually denoted by m, and a column for every point x. And I put 0 or 1 here depending on whether this point belongs to this range or not. Okay, so this is an incidence matrix for a given x. And then what do we want to compute in the range counting problem? For this x, for the set of weights of the points, we just want to output product of this matrix of size m by n with the vector of weights. That is, for every range, we just want to sum up the weights of the points inside this range. Okay?
So x's are like a data to the data structure, or
these both are inputs, just different kind of inputs. Those are say coordinates in the plane, and this is their weights.
I see. And the r's are the place.
Mm-hmm. Yeah, and here in the group we have many efficient data structures for different range counting problems. For example, one of the most famous examples of this problem is orthogonal range problem, where all ranges are just axis-aligned rectangles in 2 dimensions or in some d dimensions. And there we have very efficient data structures. There are, say, some range trees what is interesting about this data structure is that all what they do is they sum up the weights. They don't even subtract the weights. Just they sum up the weights, and they're pretty efficient. For slightly superlinear space, we have extremely efficient data structures. For really linear space, we have not so efficient data structures. So the query time is polynomial. And this group and semi-group model, they both were actually introduced to say that, okay, these data structures are optimal at least as long as you're just summing up, subtracting weights. All of them, like that's what they're doing, say range trees and similar data structures, and apparently this is not sufficient this is not sufficient set of operations for more efficient data structures. For example, in 1989, Chazelle proved very strong polynomial lower bounds in the semi-group model. He says that I allow you to do whatever you want with the coordinates of the points. I just don't even count these computations. But if you only sum up the weights, then your running time will be large. In semi-group model, he proved very strong polynomial lower bounds in the query time for various natural classes of range counting problems. And today we want to prove strong lower bounds in the group model, in the stronger model, where you can sum up and subtract them. Okay, so more formally, a range counting problem is given by a bunch of ranges. A data structure is, again, preprocessing and query functions. And we say that there exists an ST data structure if I allow you whatever computations you want to make on the coordinates of the points. I'll only charge you for working with the group elements. So ST data structure, space S query time T, would just take this n weights, preprocess them into S elements of the group, and then each query looks at this S preprocessed elements and computes the answer to the query. And so all what I'm saying is that all answers are correct. They're exactly the product of the incidence matrix and the vector of weights. And every query function only looks at T memory cells or their negations. Okay? Make sense? So same model. In a sense, I allow you I allow you to do whatever you want with the coordinates of the points, but I charge you for every kind of group operation. All right. So we want to prove that even in group model, not only in semi-group, but even in group model, we can prove strong lower bounds. What does it mean? That means for linear space, we will finally prove polynomial lower bound on T, on the query time. For like stronger models, like self-proper linear model, we can only prove logarithmic lower bound on T. Here we'll prove polynomial, and to some small extent. Any questions? Okay, so it's also important what kind of ranges we have. Ideally, we would like to prove it for natural range counting problems, like maybe this rectangles in 2 dimensions, in 3 dimensions, and so on. We don't know how to do this, but in general, our ranges won't be too scary. There is a formal notion of complexity of a set of ranges. It's called semi-algebraic complexity. I don't want to introduce it here. It just says that you want to be proving lower bounds for regions in as few dimensions as possible, and for as simple regions as possible. For example, ideally, you would prove it for regions in 2 dimensions, and regions are maybe convex polygons with 5 edges, with 10 edges. The simpler your regions are, the better your lower bound is.
What are the memory elements allowed to contain?
Yeah, so it's a group. So all what you can do is a group operation. Do whatever you want. Like you have n input group elements.
So it's an arbitrary sum.
Yeah. And for example, you can compute 1,000,000 times the first element plus 3,000,000 times the second element, because preprocessing is still unbounded. But yeah, those are sums. And yeah, obviously you can use the negation as well. That's a group model. That's what makes it much stronger than the semi-group model. You can use negation. For semi-group models, there are simpler covering arguments that say that, yeah, if you only sum up things, never subtract, you cannot actually have very efficient data structures for range counts. Make sense?
Why is it weaker than a linear model?
Formally, it's not, because you can do like in linear model. Okay, in linear model, query can compute million times the first memory cell in one operation. Here, you would spend many operations for this. You don't have million anymore. You have black box that performs group operation.
You're allowed to have arbitrary linear combinations in the memory cell.
Right.
But you can only add up, you pay to use the memory cell.
Exactly. Yeah. Yeah. And we're going to exploit it like crucially. Yeah, this is going to be crucial.
Will it cost me a lot though, because I can do like a repeated summation?
Yeah. So here I would say, like, you show me T memory cells, you're gonna yeah, it will cost you 1 million. Like you are allowed to take linear combination of the memory cells, say pi times I don't know, epsilon I. Epsilon I is a plus or minus 1, and the total number of such operations must be T. Right, more questions?
So I didn't understand what the...
Every query is a sum of at most T memory cells, possibly negated, possibly repeated.
But with the...
You pay for repetitions.
With the information that I collected, I can then do internally whatever I want?
No, you can't even perform like kind of group operations without me. Yeah, no.
I see, okay.
You can do whatever you want as a function of the coordinates. So, yeah.
So you cannot do anything?
You don't even know the group. I'm the only one who knows the group. When you if you're a data structure designer, you say, I have a data structure that works for every group, for every X, for every W. So I'm giving you the list of ranges, and you say, here is a data structure that works for every group, every X, and every W. So you don't even have the group description. You want to do a group operation, you ask me.
I see.
So could you go back to the previous slide? No, sorry, I can't wait. That's one point. So the query, we speak about the queue. So is it the data structure described by Q and Q?
Yeah. So this preprocessing function, it takes the input. Yeah, and this is query. That means
So those are all the allowable queries? There's M?
yeah, you compute all M outputs.
Why
Yeah.
does it take RD to M?
Oh, you like because you can do whatever you want with the coefficients of the points. If you need the coefficients of the points, you can look at them. This is a range counting problem. That is, there are two kinds of inputs. Points, say, in the plane, and each of them has a weight. Weight is from the group. Now, so the problem looks as follows. There are a bunch of points in the plane and elements of some group, a weight for each of them. My range, each query is a range. Sum up the weights here. Yeah, okay.
Every query can know about every single location of the
Yeah.
Sorry, I'm not done with you. So if I do the linear model over a small field, then is there any difference between, does that fit into the group model?
It does fit for like F2.
So does that mean lower bounds?
No.
Group model applying to lower bounds?
So in the linear model, isn't it assumed that the group is known? And
Sasha,
here the
it's
group
That
is
the
not
weights.
known?
In linear model, oh, I see. So you're saying, that's what you're saying.
If it's
In
a
a
small
small-
field,
in a
it's a
small
constant
field.
size field.
No, but no, I think the proof of
No, it doesn't give.
no, right, but the point is that You somehow need.
Yeah, no, our proof will give a lower bound for a group, for a field which is not small.
Exactly.
It will only work for fields of size 2 to the n log n and larger. Once again, when you are a data structure designer in the group model, you tell me, I'm showing you my n cube, very fixed, explicit rectangles,
I see.
and you say,
Your algorithm doesn't know the group.
yeah, your algorithm doesn't know the
Every
group, and I'll give you a group. It will be huge. It won't be a F2, where your algorithm definitely fails.
The proof inherently uses a huge.
Yeah, well,
so it won't work for.
Unfortunately, yeah. Otherwise, yeah, it would imply lower bound in the linear model, but and possibly a circuit lower bound, as we just saw. Yeah. Okay. Good. So the main result here is that we'll give an explicit set of n cube ranges, such that any data structure in the group model with linear space must use polynomial query time. Okay. So the lower bound, that was essentially our dream. The lower bound is good. The number of queries is reasonable. Just in cube we can actually decrease it a little bit if you want, but it's like anyway reasonable. Our queries are ranges in the plane, which is amazing. The only thing we don't like about this result is that our queries are convex polygons with very simple description, but they have like even super polynomial number of edges. Sub-quasi-polynomial, but super polynomial. It's n to the log squared. So that's a thing we don't like. We would really love to improve it. We don't currently know how to do it. No, there are n-cube queries. They're fixed in advance ranges. They're convex polygons in 2 dimensions, but unfortunately our convex polygons have n to the log n vertices. So they're not natural queries. Prior to this work, we didn't even know how to prove it for, say, polygons with 2 to the n edges. Here, like along the way, we'll prove it for polygons with 2 to the n edges, but later we'll bring it down to n to the log n square. Still, that's like, we would love to have much more natural ranges. Sorry? Yeah. No, there are many things we would like to improve, of course, yeah. In semi-group model, actually Chazelle can prove strong lower bounds, polynomial lower bounds, even for superlinear space. Yeah, that's another thing. Huh? Yeah, exactly. Yeah, where you don't have negations.
But you want to show the full time-space trade-off?
Sure. So Chazelle essentially proved.
What this theory gives, right?
I mean, yeah, what we prove here is the following. T to the s, where should I write it? T to the s must be n to the order of n. Yeah. So when s is linear, t must be polynomial. Okay, I'm going to be reusing this slide. This is going to be my proof outline. I'll be adding items one by one. So how do we prove you have a question, Mike? Oh, no. How do we usually prove a lower bound in a computational model? We usually say we find some property such that efficient computation has this property, and now we present a problem that doesn't have this property, hence a lower bound. So we want to find some structure in efficient data structures or in problems computable by efficient data structure. Here is our property. For a set of elements of, say, group ZP, our lower bound will hold even in very simple group ZP for a very large P, very large prime P, which will be like 2 to the n log n. So we'll be working only with ZP, which is like nice abelian group. So a subset of elements of ZP, we call it diverse if the following holds. Whatever Q you pick from 1 to P minus 1, if you multiply all the elements from the set by Q, then at least one of them is not close to 0 modulo P. Let me show an example.
Can I just ask one more question?
Yeah.
Sorry for going back. So you said like if you were able to prove lower bound over a field which is too small,
Yeah.
that would imply lower bound for the linear
Exactly,
model.
yeah.
That's only because you deal with only abelian groups here. If you were to deal with like any group, could
Yeah.
you show a lower bound for a smaller group but non?
No, not not necessarily. Yeah, you need some ring to work with a linear problem, right? So yeah, if you're it just happens so that our lower bounds is always EP, which can be embedded in a field. But yeah, if you prove it for a different domain, that it does not necessarily immediately generalize to linear.
Okay.
Yeah, yeah. So a set is not diverse if, like, say this numbers from 0 to p minus 1. If I can multiply it by some q, and all elements will be here, will be very close to 0 modulo p. That's not diverse. Diverse means whatever q I multiply it by, I always have an element in the middle somewhere. Okay? So here is an example. This set, say p is 89, I have this set. Apparently this set is not diverse because when I multiply every element by 13, all numbers are very close to 0 or very close to 89. So this is not diverse, right? There is some q which witnesses it's not diverse. Everything is close to 0 modulo p. On the other hand, this is always a diverse set. Why is it so? Because assume you want to prove this set is not diverse. You give me some q, and you claim that if I multiply q by 1, it's close to 0, by 2 is close to 0, by 4 it's close to 0, but at some point you'll come here, which is like p over 4. This is 3p over 4. You multiply it by another 2, you cannot jump all the way here. You'll have to jump in the middle. So this set is not diverse, for example. Oh, it is diverse, sorry, it's diverse. Okay? Okay, so we want to say efficient data structures are not diverse, and then we'll find a problem which is diverse. That's it, we're done. That's lower bound. What we mean by efficient data structures, we mean the following. So data structure takes inputs, preprocesses them into memory cells, and computes some outputs. We're saying in the group model, for every input, the set of answers to queries, the set of outputs, is always not diverse. It's never diverse. An efficient.
Are we restricting now our group to be a ZP?
Yeah, it's going to be ZP. Moreover, P must satisfy some condition. Yeah, we'll prove it now. Yeah, I'm just saying what we're going to prove. We're going to prove that every efficient data structure has its set of outputs is always not diverse. Okay? Then I'll find some range counting problem that for some points in the plane and for some weights must have diverse set here. So your data structure cannot compute it. Yes?
I remember reading this paper. I really loved it. Is there any intuition where this idea of diverse came from? It's easy to say afterwards. But
Yeah, let's do it in 2 steps. Thank you. Okay, let's prove that efficient data structures are not diverse. That's easy. So we want to say for any data structures, as long as P is very large, M outputs are not diverse. So we want to say that there exists some Q such that after multiplying by Q, all elements are almost 0 modulo P. So here's my data structure. I want to say all M cube queries can be multiplied by Q and become like almost 0 mod P. I don't know how to do this. But I'm going to use the fact that each query is a sum of only T elements. So if I make this element small modulo P, then their T sums will still be small modulo P. Instead of making N cube elements small modulo P, I will make N elements even smaller modulo P. And that would be sufficient. So I will say that there exists some Q such that memory cells, when multiplied by Q, are very close to 0 modulo P. Make sense? And this is just a standard Dirichlet approximation.
But wait, this is where you use the TS. I mean,
It's
if you
a
had
sum of
large
T elements.
coefficients, this would be now gone.
Well, exactly, yeah. That's the only place, in fact, where
That's
we
the
use it.
only
Yeah,
place.
that's the only place, yeah. Okay. Mhm. Yeah. So I want to say, as long, for large enough P, I can make this S element small modular P, and this is Dirichlet simultaneous approximation. I just say, whatever you write in S memory cells, let me try to multiply it by 1, by 2, by 3, by P minus 1. I have P different vectors. I can just partition these vectors into groups such that the first group of vectors has the first element, it has elements of this form. X1 must be from, say, 0 to P over 4T. X2 must be from 0 to P over 4T, and so on. XS must be from 0 to P over 4T. Second group will have elements, will have vectors where the first element is from the same range, second from the same range, but the last element is from the next range, and so on. Since P is so large, I will have two of these vectors in the same group. When I subtract them, this is a standard like pigeonhole principle. When I subtract them, I have that all the coordinates are very small modular P, because they belong to the same group. So all the coefficients are very close to each other. So if I multiply my vector by the number I minus j, then yeah, I get that all the elements become very close to 0 modular P. Just pigeonhole principle. Okay.
And the axis on the whiteboard is based on the slide.
Sorry.
Okay. Good.
Okay. So if P is large, then every output of every efficient data structure is not diverse. Okay. Recall that we want to prove, say, lower bound for linear space. We want to prove a polynomial lower bound on T. And this implies that P must be pretty large, at least 2 to the n log n, just for this to hold. P must be at least 2 to the n log n. Okay. Now we just want to find a data structure problem such that for some inputs, not necessarily explicit, for some weights to these inputs, again, not necessarily explicit, the outputs form a diverse set. That would mean that your data structure cannot solve it on all inputs. In fact, our inputs and our weights will not be explicit. We prove their existence. So we know that your data structure cannot solve my problem, but I don't know why. I just know that there exists an input where you fail. Okay? I just need to find a problem where output is diverse. I know a diverse vector, but I don't know any data structure which would produce this output. We already saw that this vector is always diverse, but I don't know any data structure problem that takes n inputs and from their weights creates this at least n log n outputs. So I know very simple diverse vectors. I just don't know how to embed them into data structure problem. So now my goal is to find a data structure problem whose output is at least sometimes
Yeah, so
diverse.
I think I don't quite understand what it means to embed a diverse set.
In data structure problem, every output will be sum of some inputs. Every output, maybe like n cube outputs, each of them is a sum of the n inputs. I don't know what sums of n inputs would ever produce this n log n outputs. I couldn't find such a problem. If I had like n log n inputs, yeah, I could get such n log n outputs. But from n inputs, I don't know how to get this specific set.
So, question. So if you can actually find an explicit set of weights,
Yeah.
such as there's a problem and then by summing up different subsets of these weights, you can actually get 1, 2, 4.
Yeah, yeah,
to the log
that would be
of-
amazing, but you still need to embed it into some range constant.
Yeah, I mean, this mean that even if I tell you that my problem is this input,
Yeah.
just this particular input you need to solve, you
Yeah.
still don't have a data structure that does it.
No, no, it's still not sufficient. It doesn't matter if X or W are explicit or not. It doesn't change much, yeah.
Okay.
Yeah.
It just feels a bit strange to me because now you just have one input
Uh-huh.
that and you know this particular input.
Yeah. Okay. Okay, now we'll prove that in order to get diversity, it's sufficient to get, I recall this, for the range constant problem, we have for every input incidence matrix. So R is a set of this, say, n cube ranges. For every set of points x1, xn, each from these d dimensions, we can create incidence matrix, which is just n cube by n01 matrix. I have 1 if this point belongs to this interval. I want to say that if for some x, again non-explicit, incidence matrix is sufficiently independent, then I'll find a non-explicit weights W such that the output of the data structure will be diverse. This is the output of a data structure. So I'm just saying that if you give me sufficiently independent matrix, I'll find weights that must produce diverse output. And an efficient data structure cannot compute it. So this is just like a thought experiment. If our M outputs to the queries were completely random elements of the group ZP, then it would be easier to see that with high probability they are actually diverse. If all our M outputs are completely uniformly independent elements of the group ZP. But this is not the case. There are some sets of the input set of size n. I cannot have, like, I don't know, some n log n completely independent elements in the sum set. The best I can hope for is that my outputs are partially independent. The best I can hope for is that my outputs have order of n wise independence. And then, like, instead of Chernoff bound, I can use some Chernoff bound for k-wise independence, and actually, apparently, this is sufficient. Apparently, if you get this matrix for some vector x is n wise independent, I mean n over 100 wise independent, which means every set of n over 100 rows has full rank, then there exists a set of weights that by Chernoff bound guarantees you that the output is diverse, so not computable by an efficient data structure. All what I need to do now is, for my not yet defined ranges, prove existence of an X where the incidence matrix is k-wise independent. But do such matrices even exist? Let's talk about this. I need to find a k-wise independent matrix of size n cubed by n with zeros and ones. So first of all, if I want to prove they exist, I would like to say, okay, I take union bound over all k by n submatrices. Each of them, if my matrix is random, each of them is full rank with high probability, all but 2 to the minus n. And I would like to say that that implies that a random matrix is order of n wise independent. But no, this approach doesn't work. Union bound doesn't work here because you have super exponentially many submatrices of size order of n times n. So union bound doesn't work here. We'll have to do something else. I just want to know that if we didn't require the matrix to be 0, 1, it's super easy to get n-wise independence. Take Vandermonde or like any Fourier matrix, anything. They're completely n-wise independent. but we want all entries to be zeros and ones. I can take an ECC, I can take an error correction code over F2, it will be 0, 1. It will be linearly independent over F2, so it will be linearly independent, say, over the reals for sure, even more linearly independent over the reals. But there is a bound, like the best k-wise independence over a finite field you can get with polynomially many rows is n over log n wise. And this is not sufficient for our lower bound. For our lower bound, we really need n-wise independence. So prior to this work, we didn't even know such matrices exist. Is there a 0, 1 matrix which is order of n-wise independent? If it's not 0, 1, yes. If it's n over log n-wise independence, yes. But there are such matrices, yeah. So yeah, here we prove that a random matrix does satisfy this property. But yeah, we cannot just do union bound. We have to do some chaining.
So is it over, just over R? Or?
So here, for simplicity, I do it over R. But we prove it for large enough fields. In fact, the field size must, for large enough fields. Yeah. A field must have at least polynomial size for the following reason. So if you think about best error correction codes, or like best k-wise independence that you can get when M is polynomial in N, not linear, the best you can hope for and the best we can achieve is N over log of N base field size. This amount of independence you can achieve using like best error correction codes, and Benioff and others prove that this is actually optimal. So if your field has smaller than, say, polynomial in N size, you cannot hope to get n-wise independence. So your field size must be at least, I don't know, square root of n. Okay, Omri, should I wrap up or when should I finish?
I think we can fit. Do you plan to sketch the?
Oh, sure, I'm happy.
So I think we can sketch the proof here for like 5-7 minutes, and then the randomization. I think we can just.
Okay, so let's prove that a random matrix is n-wise independent over, say, the reals or large fields. Yeah, so we prove it. It has some applications in compressed sensing, but let's ignore this. In order to prove this, we just use some anti-concentration inequalities. Say Littlewood-Offord lemma, which says that if you have fixed x and then take their, say, plus minus 1 sums, of course the expectation is 0. You're going to hit 0 often, but not too often. The probability that you hit exactly 0 is at most 1 over square root of k. And there are versions of this lemma over finite fields. This version is super easy to prove. This is an exercise over finite fields. It actually requires work. Okay. So now, how do we prove that a random matrix is order of n-wise independent, say over the reals?
Sorry, what's the lemma over finite fields? The same?
Littlewood-Offord works over finite field as well. We need this result over finite field.
But what is the field size?
For any p, it actually works. But look, what's the probability that you hit 0 in a field of size p? It's at least 1 over p. So when you do it over finite fields, you essentially add 1 over p here. Yeah. We need this result not over the reals, but over finite fields large enough. So we need to use like Littlewood-Offord over finite fields. It adds some 1 over p, but it doesn't matter much for us because p is very large. Okay, so I want to prove a random matrix like this with zeros and ones is k-wise independent. How do I do this? Assume it's not. Let me find the smallest number of rows which are linearly dependent. Say these I rows are linearly dependent, but every set of I minus 1 rows is linearly independent. So in particular, these I minus 1 rows are linearly independent, and there is a full rank matrix. Okay? It's full rank, so it spans all of this. In particular, there is a unique linear combination of these rows that gives me this orange part. It's a basis. There is a unique linear combination that gives me this one orange row. Okay? But also, since I assume those are not linearly independent. This part of the matrix must satisfy exactly the same linear equation. And Littlewood-Offord just tells me that random entries satisfy a fixed linear equation with very small probability. This essentially buys me some extra pulling in factor here. And now I can actually do all sorts of, once I have this bound, I can do all sorts of union bounds. So all choices of this I-1 rows of this I-1 columns already have a very, very large, like very small probability of this event by Littlewood-Offord.
Could you repeat the argument?
Yeah. So the trivial union bound doesn't work here. So how would I like to prove it? I would like to say that I have a random 0-1 matrix, and every submatrix of size k by n has full rank, has a rank k. So I would like to look like a random k by n matrix has full rank with probability all but 2 to the minus n. Because with probability 2 to the minus n, the first two rows are just identical. But the number of matrices I would like to consider, submatrices, is super exponential. The probability 2 to the minus n is not sufficient. I want to have this probability 2 to the minus n log n. Then I would do union bound. That's what Littlewood-Offord gives me. Littlewood-Offord, here's how I use it. I say, assume this matrix is not full rank, and assume I is the smallest linear combination. In particular, this I-1 rows are full rank. So there is some I-1 by I-1 full rank matrix. These rows give me a basis. So the remaining, the ith row, is a unique linear combination of these guys. I assume this I rows satisfy some linear equation, so this part must satisfy this equation as well. But those are random 0-1 entries. Probability that this satisfies a fixed linear equation, this satisfies a fixed linear equation is very small. By Littlewood-Offord, this satisfies a fixed linear equation with probability 1 over square root of phi. Each of them satisfies it with probability 1 over square root of phi raised to the power n. And like the hardest interesting regime is when I is like polynomial in n, but in this case, this probability is 2 to the minus n log n, which is what I wanted for the union bound.
So why is this a random linear combination?
The thing is that linear combination is not random. It's fixed by this part of the matrix.
Yeah.
But then I sample those entries independently. They cannot satisfy this fixed linear equation with high probability. But yeah, when I do union bound over then this part of the matrix, these events are not completely independent. I have to do some conditional probability. But yeah, that's the idea. Littlewood-Offord buys me extra log n factor in this probability. Yeah.
Sorry, what was not completely independent?
Yeah, no, I would like to can we take that offline?
Yeah.
Yeah.
So just what I understand is you first choose the full rank matrix, now you fix it, and conditioning on this fixing,
Yeah.
you get this
Yeah.
probability.
Yeah.
It's just an analysis, yeah.
Yeah. Okay. So that's how we prove that a random 0-1 matrix is good, satisfies the properties that we need, and a random matrix would lead to a range counting problem, which is like really bad. It would have, it would be polygons with exponentially many edges. We don't want this, so we'd randomize it. We'd randomize it as follows. In our proof for random matrix, the only property we used is Littlewood-Offord. I don't need completely uniform random bits. I need bits that are full hyperplanes. Such that instead of random bits in the matrix, it's sufficient to have bits that would satisfy this equation with probability roughly 1 over square root of k. I don't need completely uniform bits. It's sufficient to have bits that are full hyperplanes, this kind of equations. And we do have PRGs for hyperplanes. They have almost optimal seed length, log n times log n squared. Yeah. So instead of generating a matrix completely at random, I can just take the columns of a matrix as outputs of a pair G against hyperplanes. I save a lot of random bits this way, and then finally I can say that this can be embedded as some range counting problem actually in the plane. If my pair G has seed length R, which is log n times log n squared, then I just put some 2 to the r points on a circle, for example, doesn't matter where I put them, and define n cube regions as follows. The first region, just every point corresponds to a possible value of a seed of the pair G. The first region connects all seeds on which pair G outputs the first bit 1. Second region is all the seeds where the second bit of the output of pair G is 1, and so on. I have n cube ranges for which I'm proving lower bound. So in short, this is n cube ranges. By k-wise independence, I know there exist n points. By this little what offered, I know there exist n points that give me k-wise independent incidence metrics, and then I know that a random set of the weights of these points would actually imply a diverse output of a data structure. All right, so that's it. That's the sketch of the proof. We get this n cube very explicit queries. We don't like that the number of edges is super polynomial. And in fact, like the half of the paper is our program to how to potentially make these queries nice, maybe hyperplanes or some other nice regions. But yeah, we don't know. We currently don't know how to do this. All right, that's it. So we proved some limitations for these two models. We proved some polynomial lower bounds for these two models, and that's the end.
Questions to Sasha?
Quick question. So
Yeah.
the trade-off you wrote there was something like t to the s is at least n to the n.
Right, right, yeah. T to the s, so what we prove here is t to the s must be at least n to, I don't know, n over 70, for example.
Okay, so this also means that when the space is n log n, you don't have a time lower bound.
Yeah.
But also, on the other hand, like cell sampling does give you some non-trivial time lower
Yeah.
bound in this region.
Yeah.
So is there
Yeah.
a hope to?
We don't know how to do it. Like it's, we don't actually understand how it happens. So, like to prove any lower bound, we have to work with a group of size n log n to prove any data structure lower bound. To have the properties that we need, P must be at most 2 to the n over log n. And like we really don't have any freedom there. Like no, we don't know how to get any other trade-off. Yeah, how to move it anywhere. Yeah.
Any questions? Great. So let's thank Sasha again.